Swayam Prabha. Digital India. Educated India.
Namaskar. This is Ramanathan from the Department of Chemistry and IKS Center of Excellence, IIT BHU, Varanasi. I'll be introducing IKS in Chemistry, Metallurgy and Material Science today. It was William Ramsay who said, "The country which is in advance of the rest of the world in chemistry will also be foremost in wealth and in general prosperity." Now, his words has been independently corroborated as well as validated by Angus Maddison, whose 2000 years of analysis of the world GDP and contributions by different countries revealed the fact that for more than 1.5 millennia in the past, India has been in the top contributors to the world GDP. Now, correlating William Ramsay's words and Angus Maddison's data, we can safely conclude that it was the advancement of our ancestors in India in fields like chemistry, metallurgy and material science that generated wealth to such an extent that it attracted visitors as well as invaders from all across, and that's what we have studied and seen it in history. So the contributions of our ancestors in this field it's very important, and through this introductory lecture we'll get an overview of what have been the prominent contributions. But before that, whenever we look at the Indian knowledge system, be it in any subject, there are three distinct approaches that one may adopt, and they are historical, text-based or concept-based. Under historical, one may look at events as chronology unrolled, then correlate that with allied fields, and particularly in the field of chemistry and metallurgy, we can correlate that with archaeology. Elsewhere in other subjects, it can be correlated with linguistics and other developments. Text-based, we can take a prominent text pertaining to this field and look at the textual understanding analysis and compare it with what is understanding today. And in concept-based, we can see what change in the perception of concepts in that particular field has changed over a period of time, or has it remained the same. And in this introductory lecture, we will get a glimpse of all these three approaches in the coming slides, which I have broadly broken down into these categories, namely introduction, then we'll be looking at the metallurgical heritage, one example from the concept-based approach, then the textual approach, and under the combining the textual and the conceptual approach, looking at this gold rush, and one example of cross-disciplinary approach, how we can have combinatorics from the Indian tradition that pertains not necessarily to the mathematical text. Now let us look at the metal heritage of India, and Vedas being one of the earliest corpus of literature from our country. This is an excerpt from the Krishna Yajurveda, Taittiriya Samhita, where we see the following 6 metals being explicitly mentioned. Hiranyan chame, yashchame, sisanchame, trapushchame, shyamanchame, lohanchame. So where we see Hiranya, Aya, Sisa, Trapu, Shyama and Loha being explicitly mentioned, which translates to gold, silver, lead, tin, copper and iron. Now, this is in slight contrast with the anthropological division of the timeline vis-a-vis Stone Age, Metal Age, and within them, when we say of the Paleolithic Age, Mesolithic Age, Neolithic Age, and then the Bronze Age, and then the Copper Age. And then actually comes the Iron Age. Copper Age, Bronze Age, and the Iron Age. But so here, that sequential timeline, if we were to take it on its face value, we would have to conclude that this verse, which talks about copper and iron at the same time, should have been composed at a much later stage. Or if we go by the mainstream, go by the traditional timeline associated with Krishna Yajurveda, then this classification, anthropological classification, actually will not be valid. But be that as it may, here we get for the first time explicit mention of the 6 metals in one go. Going a little bit early, fast forwarding to the Samhita period, which is the Arthashastra Kala, one of the again earliest text after the Vedic literature corpus, we get to see in the second Adhikarana of Arthashastra, which otherwise is normally attributed to a text in political science or economic welfare. In the second chapter, we get descriptions of metals, starting from gold, silver, copper, whatever metals that was available and that were processed during Arthashastra's time. We get its occurrence, purification processes, processing them into different usable materials in the second chapter. One example here that is flashed on the screen is about the occurrences of gold. Jambunadam, Shatakumbham, Hatakam, Vainavam, Shrinkashuktijam, Jatarupam, Rasaviddham, Akarodgatam cha Suvarnam. So these are the different varieties of gold that Arthashastra talks about, and in the remaining verses it talks about the qualities, properties and natures of each of these gold varieties. Fast forwarding to iron from gold, this is a summary of the archaeological artifacts of iron that has been excavated at different places as gleaned from the monograph written by Panchanan Niyogi some roughly 100 years back. The purpose to impress upon the fact is that from north and south to east and west, we see the iron artifacts that have been excavated are more or less identical in their metallurgical profile, which means the iron processing were more or less similar, which could happen only either if there is a pan-Indic knowledge spread across the India about iron processing, or there was a centralized method where the iron was getting processed and it was getting distributed. The chances of the latter being very slim. It is only the former that is logical and plausible, which goes for the fact that the metallurgical knowledge was pan-Indic, and it had the pan-Indic nature of this metallurgical knowledge is reflected from the archaeological artifacts. The famous Mehrauli iron pillar stands as a testimony to the quintessential metallurgical knowledge, particularly with respect to iron, because with respect to iron, we have a common day-to-day experience today that in no time, within a couple of weeks, the iron artifact starts to get rusted. Rusting process kicks in quite quickly. That is what we see today. But here we have a specimen of iron pillar standing tall, which is at least estimated as old as 1500 years from now, and it has stood the test of time and weather, and it has not yet rusted. So it is still there for people to go and see, and there have been much scientific research done on its anti-rusting properties as well as its various features, so one can have a look at it. The other major iron artifact which has attracted the world's attention is this Damascus sword. Quite popular at its time when it was at the helm of its use, for it had all the ideal properties that a sword should have. That is, it is lightweight, light to carry, and it is very sharp, it is durable, obviously anti-rusting. So all the desirable properties of a sword which should be quite active in a battlefield were all satisfied by this Damascus sword, which was made by a specific kind of steel called the Uds steel. Uds is an anglicized form of the word Urukku, which comes from the Tamil origin. Urukku in Tamil becomes Ukku, and that Ukku ultimately becomes Uds in the English tongue, and it has been referred in the literature as Damascus sword made of Wood's steel. The testimony of its glory can be inferred from this beautiful imagination of a painter. The portrait hangs in the Steel Authority of India Limited office at Ranchi, where the encounter between Alexander and Puru is quite beautifully captured, where King Puru is seen to be gifting a sword made of Wood's steel, that is Damascus sword, to Alexander. And behind King Puru is his subordinate, who is carrying apparently a golden chest, and inside it having a steel brick. So we can see how this steel produced in India back then was valued even higher than gold, that a steel brick was being gifted by placing it in a box made out of gold. Moving to the next metal, copper. These places again are gleaned from the work of Panchanan Niyogi, who wrote another monograph on copper, namely Copper in Ancient India. So we can see the ubiquitous nature of copper metallurgy in our country from the number of places where the copper metallurgy was being practiced, and standing as a testimony to this exquisite copper metallurgy is yet another standing statue of Buddha, excavated from a village called Sultanganj in Bihar, somewhere in the middle of 19th century, which has stood the test of time, has not rusted yet, and currently it is not within the country but is being placed in the Museum of Birmingham. Copper also is another metal which undergoes rapid rusting, and those of you who have had the habit of wearing any copper bracelet or bangle would have experienced that in no time today it gets discolored due to oxidation process. But here we have another exquisite example of copper metallurgy which has resisted rusting. Talking of alloys of copper, there are two prominent alloys. One is the bronze, where copper is mixed with tin to get bronze, and right from the Harappan age, which you see from the dancing girl motif, quite well celebrated even in our school history textbooks, we see from the Harappan dancing girl to the Chola bronzes that are still made out in a place called Swamimalai in and around the area of Tanjavur in Tamil Nadu, where the making exquisite bronze artifacts with fine nature of details in the figurines and the statues are still in vogue, and this fine nature of artwork can be seen right in the Harappan age, looking at the stack of bangles in her left arm, and on the middle image you can see the sari of Saraswati being shown in the leg and the thigh region. And these were the levels to which these alloys, particularly bronze, was handled by the metallurgists of yore and even today. And interestingly, the process also that was formed, that was adopted to make these artifacts are still continued, which is called the lost wax method or Madhuchisthana Vidhi. Another prominent alloy of copper is brass, where copper mixed with zinc results in brass. And brass in our Sanskrit literature is referred to by various names. One of the names is Pittala, and here I am showing the antiquity of this brass by quoting Atharva Vedic verse where it says Tadaha Vaishvananam Pittalam Tadashvina Viveshatamiti. So similarly you have it. There are other names of brass, namely Riti or Ritika, Pittala, Arakuta, Ara and Swarnaka Krita. Another reference from Katyayana Shrauta Sutra, where you get the occurrence of Pittala. Then this is from the again Katyayana Shrauta Sutra, where you get another synonym for brass, that is Suvarna Krita. Now, talking of the formation of brass, even today, there are two broad categories by which brass is formed. One is called the cementation process, and the other one is the mixing process, where in the mixing process you see that the atoms of copper and zinc are The atomic sizes are nearly the same, and the formation is usually happening by substitution in the solid solution mode. So there are two types in which the brass is made, and which are called the intentional brass, and the other one is called the accidental brass. The difference being, when the ancestors in the ancient times were trying to process copper from its ore, due to the lack of technology by which they could enrich only copper ore or identify only copper ore and then proceed for processing, accidentally all other metal ores could also get combined with copper, and zinc being the predominant one and with its atomic size being nearly same as that of copper, while processing copper, accidentally zinc was also getting processed, and that's how accidental brass was getting formed, and that is what is referred to as accidental brass. And in such a condition, the zinc content in the brass cannot exceed 12 to 13%. Whereas in the intentional brass, there are instances where even 30 to 40% of zinc can be observed in the brass, and that kind of a brass is only possible to be made by an intentional route, which is called the intentional brass. Then Vanda Morton in history, not very long back, in just a few years back, asked a very important question, that who first made brass intentionally and where? Because in order to make this intentional brass, one of the primary prerequisite is to have pure copper and pure zinc. So this leads to the research into the zinc metallurgy as well. Now, be it bronze or be it brass, it is not at all to be claimed that our ancestors knew the language of phase diagram. Mind you, I reiterate, the language of phase diagram by which today alloys can be readily understood and made is not known to the ancestors. So it is still a matter of great research, or we are yet to unravel the exact methodological process by which our ancestors were so successfully making alloys, not just bronze and brass, but also iron alloys, namely this steel. But definitely the knowledge of phase diagram is a modern scientific output, and at least through this lecture, it is not being claimed that phase diagram was known in the past. All that we know through archaeological artifact is that alloys were made, and how they were made, whether it was empirical or hit and trial, or they had a methodical process, is yet to be unraveled. Now, with the occurrence of intentional brass with archaeological artifacts found at Atranji Khera, where as high as 40% of zinc was found in the brass, it begs to the question of having pure zinc. So before we get into the zinc metallurgy, we need to we'll briefly have a look at the properties of zinc. It has one of the very difficult metal in the sense it has its melting point at 420 degree Celsius. Quite a low melting point, because of which in the furnaces, in the open furnaces, if it is processed, it can easily get vaporized, and its vapor point is also quite close by. And then unless we have a very closed system of processing zinc, recovering pure zinc from the purification process will be very difficult. And before we proceed to the metallurgical processing of zinc, as we saw in the case of brass having multiple names, so is the case with respect to zinc. Zinc is referred in the literature, Sanskrit literature, as Yashada, Tuttha, Kharpara, Jashada and Jasta. So in fact it is Yashada which gets converted to Jashada in some text because of the Sanskrit rule of Yajayor Abheda, where Yashada gets converted to Jashada, and Jashada by Apabhramsha, a derivative of it, becomes Jasta. On the same hand, the Tuttha, the word Tuttha, although today in the common parlance, both in various regional languages, and one of the entrances in Amarakosha in Sanskrit for Tuttha refers to actually copper sulfate. But Tuttha also has been a term used for zinc. How do we know that? In Tamil, the zinc is referred to as Tuttanagam, and by virtue of the trade connection to China from the southern parts of our country, the Chinese term for zinc is Tuttanag, which is derivable from the word Tuttanagam, and Sanskrit, having the word Tutta, has perhaps loaned it to other languages, namely Persian, Arabic, Turkish, where in all these languages it is referred to as Tutia or Tutia, etc. So this is kind of an example where we need to also take help of allied fields and not just restricting to our field, especially when today we are looking at the IKS concepts, where this was one example to say how linguistics will also play a role. Whereas language is one of the early stepping stones to our knowledge heritage of the past, it is also a stumbling block, because if there are multiple words referring to one particular metal in this case, then it is easily, we can get misguided if they are occurring with different words in different literature. So we first get a very early description of zinc processing, which I said that it is quite non-trivial because of its physical property, in this text called Rasaprakasha Sudhakara, and if we accept its dating as 12th to 13th century, around the same time is also attributed to another text, Rasaratna Samuchaya, where we get to see the processing of the zinc. In today's chemistry parlance, this is actually conversion of zinc carbonate, which is the kharpara, into zinc. So it is done, today we understand it in terms of two different steps, where first it is decarbonized, zinc carbonate is decarbonized, vis-a-vis zinc oxide is getting formed, and the zinc oxide is further reduced to form zinc and carbon monoxide. So this is what is described in the Sanskrit text when the translation provided by P.C. Ray, which is shown here. And of course, it is not in the symbolic language that our text describe about the zinc metallurgical process, or for that matter, any other chemical process. Now, for that, our ancestors had invented a very ingenious method for the closed downward distillation. So on the top chamber, on the top pot, which is shown here inverted with black in color, you have the raw zinc, which is calamine or what is called kharpara, in the top inverted pot, along with several carbonaceous material which is supposed to reduce it and make it into zinc ultimately. So the top pot is completely stuffed with the raw material and the carbonaceous material and left with a small orifice, and that orifice is facing down, opening towards another empty pot which is buried beneath the ground, and you have the top pot completely exposed above the ground. Now heat is applied from all the sides and from the top on the pot which is inverted and facing above the ground, and when the chemistry is happening due to the heat on the raw material, on the raw zinc, that zinc carbonate, first getting converted to zinc oxide and then getting converted to zinc, that zinc is actually in a molten state, and that molten state, by action of gravity, it will come down through this orifice to the downward, to the bottom pot which is empty, and where you have a large temperature gradient, whereas on the top it is couple of 100 degrees Celsius, on the bottom it is a few degrees below the room temperature. You have immediate solidification of the liquid molten zinc, and hence pure zinc is obtained from the bottom pot. So this is how this process of zinc distillation was carried out, and several archaeological excavations near Jhavarmala mines near Udaipur in Rajasthan have given vouchsafed for its occurrences. And textually, we see references from the Chinese text where they have attributed their knowledge of processing zinc, and they have attributed it squarely to India. This is from the Sui dynasty's Chinese manuscript, which comes from, which is dated from 581 to 618 in the Common Era. And this is from Thomas Craddock's work, where they have categorically done carbon dating and have established that these Jhavarmala mines from which we find the artifacts of zinc distillation have been producing many tens of thousands of tons of zinc, and they are the earliest dated zinc mines in the world and earliest known zinc production in the world. The details of which can be found in this book chapter. Now, switching on to the concept-based examples. A concept-based approach to the IKS. One example that I am trying to cite here is that of mineral acids. So we can have several questions raised which are like, what is the historical account of the use of mineral acid in India? What were the earliest references of mineral acid in ancient Indian literature, especially in the works of Arthashastra, Charaka and Sushruta? How were the mineral acids used in ancient Indian medicine, so on and so forth? So this is an example for a concept-based approach towards IKS with an example of mineral acids. So we see that normally the antiquity of mineral acid is attributed to Jabir ibn Hayyan, who is recorded to be the first person to produce mineral acid, and he is dated to around the 8th century in the Common Era, specifically with sulfuric acid. He described nitric acid as obtained by distillation with niter and copper sulfate, and it is in the Western world where John Glauber, he prepared sulfuric acid for the first time in the 17th century, and this has been the historian of science's attention towards mineral acid as far as its antiquity goes. Now, in our Indian literature, if you look, there is description of Yavakshara, which is the saltpeter, and nitric acid were known in the 16th century definitely, because in a treatise called Shukraniti by Shukracharya, there is a description of making the gunpowder. Additionally, Suvarna Tantra text, which is of the 17th century, you have again this Shankhadravaka, which is another term for sulfuric acid and hydrochloric acid, which is prepared by the mixture of saltpeter and hydrochloric acid, is described. Then, of course, Aini Akbari, which is quite few centuries earlier, where description of saltpeter and acid arising from that is described. And this is the timeline with respect to some of the Indian documents as well. Now, if you slightly go back, if you look at the accounts of description of acids in India, predominantly we get to see organic acids being described as those derived from the citrus fruits. And this has led to even Professor Acharya P.C. Ray saying that we have, however, no evidence that the acid thus derived was ever used as a solvent. This he is talking it in context of while describing what is called Vida or Vida, where it speculates the formation of in situ mineral acids and not necessarily mineral acids being stored separately or being used separately. That's why he leaves it a speculation with a pinch of doubt that it might be pointed out that Rasarnava and similar other works lay stress upon Vida, in which aqua regia may be said to be potentially present and which is fully described as capable of killing all the metals. So he has not completely written off the existence of mineral acid, which has given a scope of research in today's time to recreate those processes which describe about Vida and say that this is the formation of mineral acid in the ancient India. So, Concise History of Science in India by Bose and Subbarayappa, they categorically wrote that the earlier texts on medicine do not speak of any mineral acid. But now making use of the benefit of doubt that P.C. Ray has left, when we can look upon the older texts, in this case particularly the Arthashastra, where in the second Adhikarana that I told a few slides back about gold, where the purity of gold is being talked about, when we recreate this particular step which is described in the verse, then we get to see the mineral acid actually getting formed. So, Jati Hingulakena Pushpakasi Sena Va Gomutra Bhavitena Digdhena agrahastena samsprishtam swarnam shveti bhavati. So here Jati Hingulaka and Pushpakasisa and Gomutra, these are the three ingredients being told, which when converted in the modern language is basically copper sulfate when you dissolve it in cow urine. That is supposed to produce a mineral acid. So simply taking copper sulfate and putting it in even simple water, we can see that the pH will be reduced from neutral pH to pH somewhere between 2 to 3. So this is the conceptual based approach where we can see you can recreate some of the steps and show the presence of mineral acid in the text whose dates predate by several centuries than what is acceptable in the mainstream history of science. The details of which can be accessed from this paper. So in this part 1, we have looked at the metallurgical heritage of our country, starting from gold, iron, copper and its alloys, particularly looking at the antiquity of zinc and how India has been a major producer as well as exporter of zinc. And we have also looked at one example of concept-based approach to IKs by taking mineral acid as an example.